Now that we know how to create a scatter plot, the next thing to do is to figure out some strategies for analyzing that and building a mathematical model. The first model that we're going to look at is the line, because it's the easiest, and also because it's actually very common in the things that are investigated in experiments. To understand this line, you really need to understand two ideas called slope and intercept, and that's a lot of what this video is going to be about. The first thing you want to ask yourself before you can create a model that's a line is a line a good model? Later on, we're going to have some better tools for making this judgment, but for now, we can just use a visual check. For example, this is the beaker weight and volume experiment that we've been using in these videos. And if you lined a straight edge up, like put a ruler or even a sheet of paper along the points, you would find that they don't all exactly touch the line, but they're pretty close. And so it's probably reasonable to think a line would be a good model for this data. Here's some other data. This is the diameter of a wire versus its breaking strength that we talked about in our experimental design video. A line is probably not a great model for this data because we can see that the points, even though they're fairly close to the line, there seems to be another kind of a pattern going on here. And it looks like if the values were much smaller than a diameter of 0.04 or much bigger than a diameter of 2, we would start to deviate from that line a lot, and then that would not be a very good predictive model. Again, we'll have better tools for assessing if a line is a good model later on, but for now we'll just kind of look at it and go by a visual check. So how do you describe a line? One of the things that you need to know is what's the starting point? Where does this line start on our measurable independent variable? We call this the vertical intercept. In math classes, you've probably heard that called the y-intercept. We don't call it that, and we'll talk about y in a little bit. Another thing we'll want to know is as the independent variable gets bigger, is the dependent variable changing by getting bigger, or is it changing by getting smaller? And in addition to that, we want to know how fast is it changing? How much does it change? Does it change really quickly, or does it change really slowly as the independent variable changes? We get this information from a quantity that we call slope, which you may have heard of before in a math class. So going back to our beaker example, our vertical intercept is, it looks like 70 grams. We can read this right off of the graph. It's somewhere between 50 and 100, and it looks like it's about 2/5 of the way, so I say 70 grams. Next, we want to find the slope. And to do that, we need to find 2 points. You can pick any 2 points you want on the line. I usually try to find points that are fairly far away from each other because I think I get better results when I do that. I'm going to use as one point my vertical intercept. There's 0 milliliters of volume and 70 grams. For my other point, I'm going to choose 300 milliliters, which looks like it lines up with 300 grams. So with these two pieces of information, I'm now going to look at how are the changes occurring in both the independent and the dependent variable. In dependent first, I started at 70 grams, I ended at 300. That's a positive change of 230 grams. Now the horizontal, or the independent variable. I started at 0 milliliters, I ended at 300, so that's a change of 300 milliliters. Now that I know these two changes, I can calculate the slope. The slope is just a ratio of the dependent variable change over the independent variable change. So in our case, the slope is 230 grams divided by 300 milliliters. Now in science, we never want to leave a denominator that isn't 1. So when we see something like this, we're going to actually do the division problem and take 230 and divide it by 300. And that gives us 0.75 grams for every 1 milliliter, which is much more easy to compare than 230 grams for every 300 milliliters. Now that we have the vertical intercept and we have the slope, we can build an equation for this line. This is what it looks like. You might recognize this as being in something like the form that you learned for a line in math class, y equals mx plus b. But there are a few changes. One is we're going to use W rather than Y because Y just doesn't make sense as an abbreviation for weight. We can predict the weight by setting that equal to first of all, the vertical intercept. Now in math class B, the y-intercept comes last. In science, we often put that first because literally it's a starting point. In this case, it means what is the weight when the volume is 0. Notice it's also not just 70. It's 70 grams. Because our numbers have some meaning to them, we're going to make sure we include that unit. Then we're going to add the change. And the change is made up of two things. One is the slope, which is the rate of change. In this case, 0.75 grams for every 1 milliliter. And then we're going to multiply that by the number of milliliters, which is the volume. So again, we're not going to say x just because it's the horizontal variable. We're going to say v because v is a much better abbreviation for volume than x would be. So let's review. Find the vertical intercept, pick 2 points, find the vertical and horizontal change, take the ratio of the vertical change to the horizontal change, and that's your slope, and then never leave anything but a 1 in the denominator. So actually do the division problem, and then you can put that information together in the equation of a line. Don't forget a few things that are different between math and us. Our variables are not going to be x and y. They're going to be something that makes sense for the quantities that are being measured. Our vertical intercept and our slope are going to have units on them. They're not going to be just naked numbers. So grams in our case for vertical intercept, and grams for every milliliter, or grams over milliliters, or grams per milliliter for our slope. Stop the video and give this one a try. See if you can figure out the vertical intercept, the slope, and write an equation. Okay, the vertical intercept is the easy part. You can just read this right off the graph. It looks like it's 150 feet. Now we find 2 points. I'm just going to use the beginning and the end of my 2 points and look at the changes. The vertical axis, the dependent variable height, changed by negative 100 feet because it went from 150 at the start down to 50. In the horizontal change, the change in the independent variable, the time, was 2.0 seconds. So the slope is the ratio of these changes, so it's negative 100 feet in 2 seconds. But remember, we don't want 2 in the denominator, we only want 1 in the denominator. So we're going to express this as a decimal by dividing 100 by 2, or negative 100 by 2, and that gives us negative 50 over 1. So negative 50 feet for every 1 second is our slope. So now we know the vertical intercept and we know the slope. We can make an equation. We'll use h for height instead of y because that's a meaningful variable. 150 feet is the vertical intercept. Don't forget the feet part. Plus negative 50 feet for every second. Again, don't forget the unit. Times the horizontal axis variable, which is not x, but it's t for time. So this gives you an idea of how we use a scatter plot to build the simplest of our models, which is a straight line. This is not too hard to do, and you'll get the hang of it. And the nice thing is, because this is easy and it's very common in experimental data, science is actually not as hard as you might think.